Okay, this is magnetic flux part 2. And I was making the point here with this closed surface that when you have closed surfaces, the dAs always go normally out of the surface or perpendicularly out of the surface. And that, so if you have a line coming in like this, then the flux going through this part, this little dA here, is negative because your dA is outward and your B is that way. And so the angle between those two vectors is 180 degrees. And so if you take the cosine of 180 degrees, that gives you -1. And so basically you count the lines going in as negative and the lines coming out as positive. And then if this field is going to be straight across, would you see that the flux through if the B is just going straight like that, then this dA has no flux through it. The dAs that have the most flux through it are this guy and this guy in terms of magnitude. And the least flux is this guy. And can you imagine this being 3D? There'd be another one here. And on the other side, that would have no flux through it. Okay, but what if this is kind of radiating this way? What if it's going like this? When the field's going like that? Well, it turns out that for every arrow that goes in, there'll be an arrow that comes out. And so the total flux through here is still 0. Now, in electrostatics, the way you can get a flux, you might say, how can you ever have a situation where there's any flux in it? It seems like for every line that goes in, there'll be a line that comes out. Well, in electrostatics and in gravity, the way you do that is you put your mass or a charge in here. If you put a charge in here, then that charge the lines will start like that and they'll emanate out. And so then you do have a net flux through there. Same thing with, let me have another surface here, closed surface. That's a closed Gaussian surface. Let me put a mass in here. You see that mass? Now there's going to be field going in. And so do you see how we have a net magnetic flux going in? It's a negative flux. So that's a net negative flux. Okay, well then my last point then is this, that the way that magnetic field lines work is they're always closed loops. They never start or begin anywhere. They always are closed loops, at least so far that we have found. And so because of that, wherever I draw a Gaussian surface, whether it's right here, remember these are closed. Gaussian surfaces are always closed. And I'll make them spheres because they're easy to see, but they could be cubes or any other type of closed surface. You see how the amount of lines going in are 2, the amount of lines coming out are 2, and so the total Webers is going to be 0 going through there. Total flux. Excuse me. And that's true if I put my Gaussian surface here too. Remember, Gaussian surfaces are imaginary, so if you're wondering how I'm going to fit one in there inside the magnet, all I got to do is imagine it. That's how. And so if you count how many lines go in, let's see, 1, 2, 3, 4, 5, 6. And how many lines come out? 1, 2, 3, 4, 5, 6. Huh. So the total amount of lines, remember, if magnetic flux is proportional to the amount of lines that are going in and out, then the total amount of lines going in and the total amount of lines going out, magnetic field lines, they add up to 0. Okay. Now you might say, well, what if I were to break the magnet and get rid of the south pole? So what if I only had one pole here? Kind of like having just one charge. Good point. Then maybe you would be able to have all the lines maybe going out or something. But here's the thing is when you break a magnet in half, you just create, if I cut this in half, you create a south and a new south and a new north pole. And so you will always have a north and a south pole in there. Now, the thought is that if they ever find a magnetic monopole, just one pole, then this law might be broken. But for right now, I don't think they have found one yet. I could be wrong on that. You might do a search on Google to figure out if that's the case. But for this course, at least, you can assume that this will always be the case, that the closed surface integral of B dot dA, that's the net flux through a closed surface, will always be 0 in this course, at least. All right, that's what I needed to tell you. Thanks for listening. Bye.